In the turbulent skies of World War II, where the roar of engines mixed with the whistle of projectiles, engineers faced an invisible enemy, more devastating than any human adversary. It was not enemy bullets that brought down most aircraft, but something far more fundamental, something that attacked the very essence of flying machines. Extreme heat was destroying jet engines before they could even prove their true potential in combat. It was the beginning of a new era in aviation, a time when the limits of what was possible were being constantly redefined. The first military jets promised unimaginable speeds, revolutionary maneuvering capabilities, and a decisive advantage in the skies. But there was a fundamental problem that threatened to turn this promise into ashes, literally. The turbines of jet engines operated at temperatures that no conventional metal could withstand for long. The metals simply melted, deformed, or lost their structural integrity when exposed to the inferno of heat generated inside these revolutionary engines. American observers, experienced engineers who had worked with the best materials available at the time, began to notice something extraordinary in the late 1940s. There were reports coming from Europe about metallurgical developments that seemed to defy the known laws of materials physics. These reports were initially received with skepticism, because what was being described seemed impossible according to conventional knowledge of the time. Imagine for a moment the magnitude of the technical challenge. Inside a jet engine, temperatures can easily exceed 1200 degrees Celsius. Under these conditions, common steel becomes as malleable as melted butter. Aluminum, which had been the miracle material of aviation for decades, simply liquefies. Even the best special steels developed during the war proved inadequate to withstand these extreme conditions for prolonged periods. Engines needed constant overhauls, turbine blades failed regularly, and each combat flight was a gamble against the limitations of materials. It was in this context of desperate need that one of the most fascinating scientific races of the modern era began. A race not just between nations, but between human ingenuity and the relentless laws of thermodynamics. Metallurgists from various nations were working feverishly, each trying to find the perfect combination of elements that could resist the inferno of jet engines. But it was in Britain, in discrete laboratories where scientists worked under the weight of post-war urgency, that something truly revolutionary was taking shape. If you are enjoying this fascinating story, do not forget to subscribe to the channel and leave in the comments the time you are watching this documentary. And now, let us continue discovering how this metallurgical revolution changed aviation forever. The British had developed the first practical jet engines during the war, and consequently were the first to face head-on the materials problems that accompanied this technology. They did not have the luxury of waiting for future solutions. Their pilots were flying in aircraft whose engines could fail at any moment due to thermal stress. The pressure to find a solution was immense, and it was from this pressure that one of the most important discoveries in modern metallurgy was born. The history of superalloys, as they came to be known, is a story of trial and error, of scientific intuition and of accidental discoveries that changed the course of technology. Metallurgists knew they needed a metal that would maintain its strength even when heated to red hot. They knew they needed something that would resist not only heat, but also oxidation, corrosion, and the extreme mechanical stress of the incredibly high rotations of turbines. What they did not know was exactly how to create this miraculous material. The first experiments focused on nickel, a metal that was already known for its corrosion resistance and its ability to maintain mechanical properties at elevated temperatures. But pure nickel was not enough. It needed to be strengthened, its properties needed to be amplified through the careful addition of other elements. It was here that the true art of metallurgy came into play. Small amounts of chromium were added to improve oxidation resistance. Traces of aluminum and titanium were incorporated to create strengthening phases within the crystalline structure of the metal. Each element added changed the properties of the alloy in complex and not always predictable ways. When the first promising results began to emerge from British laboratories, the secret was kept under rigorous surveillance. Nations understood that whoever mastered the technology of high-temperature materials would dominate the skies. But secrets of this nature never remain hidden for long, especially when allies share technologies for the common good of defense. This is how American observers had their first contact with these new nickel-based superalloys. The shock they felt upon witnessing the performance of these materials cannot be understated. Here was a metal that could operate continuously at temperatures where other metals would simply cease to exist as solids. Turbine blades made with these new alloys could spin at incredible speeds, exposed to flames that would turn common steel into bright liquid, and yet maintain their shape, their strength, their integrity. It was as if the fundamental nature of materials had been reimagined. American engineers quickly recognized that they were witnessing something that would completely change the game of military aviation. It was not just an incremental improvement over existing materials. It was a quantum leap in capabilities. With these new superalloys, jet engines could operate at much higher temperatures, which meant more power, more efficiency, and, crucially for military applications, better performance in combat. A fighter equipped with engines using these new alloys could fly faster, higher, and longer than anything that came before. But understanding the impact of these superalloys requires that we understand exactly what happens inside a jet engine. When fuel is burned in the combustion chamber, the resulting gases are heated to extremely high temperatures. These superheated gases then pass through a series of turbine blades, transferring their kinetic energy to the engine shaft. The turbine blades, therefore, are constantly exposed to this flow of incredibly hot gases. But it is not just the heat they must withstand. The blades are also spinning at speeds that generate enormous centrifugal forces. Each blade is being pulled outward with a force of many tons. And all of this happening while the metal is glowing with heat. Under normal operating conditions, a modern jet engine turbine blade experiences conditions more hostile than almost any other man-made component. The combination of extreme temperature, intense mechanical stress, and chemically aggressive environment creates one of the most challenging environments imaginable for any material. And it is not enough that the material survive these conditions for minutes or hours. These blades need to operate reliably for thousands of hours, through countless heating and cooling cycles, maintaining their critical mechanical properties throughout the engine's service life. The nickel-based superalloys that shocked American observers managed to accomplish this seemingly impossible feat through an ingenious combination of chemistry and crystalline structure. The secret lay not only in the elements that composed the alloy, but in the way these elements organized themselves at the atomic scale. Metallurgists had discovered that by adding specific elements in precise proportions, they could create a two-phase structure within the material. A nickel matrix phase provided the basic structure, while precipitates of a second phase, generally composed of nickel, aluminum, and titanium, acted as microscopic obstacles that prevented the movement of crystalline dislocations, the mechanism by which metals normally deform under stress. What made these alloys truly extraordinary was that these hardening precipitates not only persisted at high temperatures, but actually became more effective at preventing deformation as temperature increased, up to a point. This was counterintuitive and contradicted everything metallurgists thought they knew about material behavior. In most metals, increasing temperature facilitates the movement of dislocations and therefore makes the material weaker. But in these special superalloys, the specific nature of the precipitates meant they continued to effectively block the movement of dislocations even at temperatures where other materials would have completely lost their mechanical strength. When the Americans began to examine these alloys in detail, using the best analysis tools available at the time, they were fascinated by the complexity of the microstructure. Under electron microscopes primitive by current standards but cutting-edge for that era, they could see the ordered cubic precipitates dispersed uniformly through the matrix. The geometric beauty of this structure at the nanometric scale hid the sophistication of the metallurgical design. Every aspect of the alloy's composition and processing had been optimized to create this specific structure. The technology transfer that followed between Britain and the United States was one of the most successful examples of international scientific collaboration during the Cold War. The Americans not only adopted the basic formulas of British superalloys, but began their own intensive research programs to understand the fundamental principles behind these materials and develop them further. Laboratories throughout the United States, both in government facilities and in private aerospace companies, began working feverishly to improve these alloys and develop new variants for specific applications. The impact on military capabilities was immediate and profound. American jet fighters of the 1950s, equipped with engines using these new superalloys, could fly combat missions that would have been impossible just a few years earlier. Engine reliability improved dramatically. The time between major overhauls increased significantly. And, perhaps most importantly, engines could be pushed to their performance limits without the constant fear of catastrophic failure due to thermal stress. But the story of superalloys was just beginning. What American observers witnessed in the 40s and 50s was only the first generation of these remarkable materials. Metallurgists quickly realized there was much more potential to be explored. If the first generation of polycrystalline superalloys was already impressive, what could be achieved if the limitations imposed by grain boundaries could be eliminated? To understand the next major breakthrough in superalloys, we need to understand a bit about how metals crystallize. When a liquid metal solidifies, it does not form a single perfect crystal. Instead, multiple crystals begin to grow simultaneously at different locations, each with its own crystallographic orientation. When these growing crystals meet, they form grain boundaries, the interfaces between crystals of different orientations. These grain boundaries are, in many respects, defects in the perfect crystalline structure. They are locations where atoms do not fit together as perfectly as within grains, and as a result, they are points of weakness, especially at high temperatures. At elevated temperatures, grain boundaries become preferential pathways for deformation and failure processes. They can slide over each other, allowing the material to deform slowly over time, a phenomenon known as creep. They can also be preferential sites for the initiation of cracks. For superalloys operating under the extreme conditions of jet engines, grain boundaries represented a fundamental limitation on the performance that could be achieved. The solution to this problem came in the form of one of the most sophisticated materials processing techniques ever developed: directional solidification. Metallurgists discovered that by carefully controlling how an alloy solidified, they could manipulate the resulting grain structure. If solidification could be made to occur in only one direction with a very steep temperature gradient, the crystalline grains would all grow in the same direction, aligned with the direction of heat flow. More importantly, if the geometry of the component was appropriate, it was possible to make only a single crystal grow, completely eliminating grain boundaries. The creation of engine components made from single crystals of superalloy was a tour de force of engineering. The process required precise control of temperatures and solidification rates. A mold containing the molten alloy was slowly withdrawn from a furnace, so that solidification progressed gradually from bottom to top. At the base of the mold, a specially designed section known as a grain selector allowed only one crystal with the desired orientation to continue growing. The result was an entire turbine blade formed from a single crystal, with no grain boundaries anywhere in its structure. The performance of these single crystal blades was even more impressive than the already remarkable polycrystalline superalloys. Without grain boundaries to act as weak points, the blades could operate at even higher temperatures and withstand greater stresses. Creep resistance improved dramatically, and reliability reached new heights. When initial tests of these single crystal blades were performed, even the engineers who had worked on their development were surprised by how well they performed. Here was another quantum leap in capabilities, as significant as the transition from conventional metals to the first superalloys. But the advances did not stop there. Metallurgists continued to refine the compositions of superalloys, adding additional elements in precisely calculated amounts to optimize specific properties. Rhenium, one of the rarest and most expensive elements on Earth, was added in small quantities and was found to significantly improve creep resistance. Ruthenium was later added to allow even higher concentrations of other hardening elements without causing the formation of undesirable phases. Each new generation of superalloys pushed the limits of what was possible a little further. Parallel to these developments in metallurgy, engine engineers were developing sophisticated cooling techniques to protect turbine blades from the most extreme temperatures of combustion gases. Modern blades are small masterpieces of engineering, filled with complex internal channels through which cooling air is directed. This air, bled from the compression stages of the engine, flows through the intricate network of passages inside the blade and emerges through small holes in the surface, creating a film of cooler air that protects the blade surface from the hot gas flow. This film cooling technique allows blades to operate in environments where the gas temperature is actually higher than the melting temperature of the blade material itself. The surfaces of blades are also protected by specialized ceramic coatings known as thermal barrier coatings. These thin layers of ceramic material, typically yttria-stabilized zirconia, provide additional thermal insulation, reducing the temperature that the underlying metal alloy experiences. The application of these coatings is itself an art, accomplished through sophisticated processes like physical vapor deposition or plasma thermal spraying. The combination of advanced superalloys, complex internal cooling, and thermal barrier coatings allows modern jet engines to operate at gas temperatures far exceeding what would have been considered possible in the early decades of jet aviation. The economic and strategic impact of these materials technologies cannot be overstated. Modern air superiority depends fundamentally on the ability to operate jet engines at increasingly higher temperatures. Higher temperatures mean greater thermodynamic efficiency, which translates to better fuel economy and greater range. They also mean greater power per weight, enabling more capable and agile aircraft. For military applications, these improvements translate directly into tactical and strategic advantages. A fighter that can fly faster, farther, and with greater maneuverability has a decisive advantage in combat. Superalloys have also found critical applications beyond aeronautical engines. Power generation turbines, both conventional and nuclear, depend on materials that can withstand high temperatures. The petrochemical industry uses superalloys in reactors and other equipment operating under extreme conditions. Even in the space industry, where rocket engines must withstand some of the most extreme conditions created by humanity, superalloys play crucial roles. Ongoing research and development in these advanced alloys represents a massive investment of resources and scientific talent. Laboratories around the world continue to work at the frontier of materials knowledge, seeking the next generation of superalloys that will push the limits even further. Modern computational modeling techniques allow metallurgists to predict how new alloy compositions will behave before they are even physically produced, accelerating the development process. Advanced electron microscopies and atomic-scale characterization techniques provide unprecedented insights into the fundamental mechanisms that govern the behavior of these materials. One of the current frontiers of superalloy research involves the development of alloys that can operate at even higher temperatures, potentially above 1200 degrees Celsius. At these extreme temperatures, even the best current nickel-based superalloys begin to approach their fundamental limits. Researchers are exploring entirely new alloy systems, including niobium-based alloys and intermetallic alloys based on titanium aluminides and molybdenum silicides. Each of these systems promises specific advantages, but also presents its own unique challenges in terms of processing and manufacturing. Another area of intense research involves reducing the density of superalloys. Nickel-based superalloys are relatively heavy due to the high density of nickel and the other transition elements they contain. For aeronautical applications, where every gram of weight saved can translate into better performance, there is a strong incentive to develop lighter high-temperature alloys. This has led to exploration of titanium and aluminum-based systems, which offer much lower densities, although generally with lower maximum operating temperatures than nickel superalloys. Additive manufacturing, or three-dimensional metal printing, is beginning to impact the world of superalloys in fascinating ways. This technology allows the creation of complex geometries that would be impossible or extremely difficult to produce by conventional methods. Turbine blades with even more complex internal cooling channels, designed by computational optimization algorithms, can be fabricated layer by layer. Moreover, additive manufacturing offers the possibility of controlled composition gradients within a single component, allowing different parts of a blade to be optimized for the specific conditions each region experiences. Sustainability is becoming an increasingly important consideration in the development of new superalloys. Many of the elements used in these alloys, particularly rhenium, are extremely rare and expensive. There is a growing push to develop alloys that can achieve comparable performance with compositions less dependent on scarce critical elements. Additionally, recycling of used superalloys is becoming more sophisticated, with techniques being developed to recover and reuse materials from end-of-life engine components. Looking back at that moment in the 1940s when American observers first witnessed the performance of the new British superalloys, we can appreciate the extraordinary journey these materials have traveled. From a metallurgical curiosity that defied conventional expectations, they became absolutely indispensable for modern civilization. Every time an aircraft takes off, whether it is a commercial jet carrying passengers around the world or a military fighter patrolling the skies, superalloys are there, working silently in the burning hearts of engines, enduring conditions that would instantly destroy common materials. The story of superalloys is also a story about the nature of scientific and technological innovation. It illustrates how urgent needs can drive fundamental discoveries. It shows how collaboration between nations and between disciplines can accelerate progress. And it demonstrates that the most significant advances often come not from sudden and isolated insights, but from the patient and meticulous work of many scientists and engineers over decades, each building on the achievements of those who came before. There is something deeply inspiring about the way humanity has managed, through careful understanding of nature at its most fundamental level, to manipulate the very atoms to create materials with properties that nature never spontaneously produced. Superalloys do not exist in nature. They are purely human creations, products of our understanding of the physics and chemistry of materials, of our ingenuity in processing metals in specific and controlled ways, and of our persistence in overcoming seemingly insurmountable technical challenges. For pilots who fly modern aircraft, the superalloys that make their flight possible are largely invisible. They intuitively trust that engines will work reliably, that turbine blades will spin at tens of thousands of rotations per minute without failing, that materials will withstand extreme conditions without yielding. This trust is grounded in decades of continuous research, testing, and refinement. Each failure observed in tests led to improvements in design or composition. Each new generation of alloys was validated through rigorous testing that simulated decades of operation in just months of accelerated test time. The integration of superalloys into modern engines represents a complex symphony of materials science, mechanical engineering, thermodynamics, and aerodynamics. Each turbine blade is positioned at a specific location in the engine, where it will face a unique set of temperature, pressure, and velocity conditions. The design of each blade takes into account not only the necessary mechanical strength, but also aerodynamic considerations to maximize the efficiency of energy extraction from combustion gases. The thickness of the blade wall, the pattern of cooling holes, the surface roughness, everything is optimized through computational iterations and physical testing. The manufacturing of superalloy components is a process that demands extraordinary precision. Tolerances are measured in micrometers. The quality of each casting is verified through multiple non-destructive inspection techniques, including radiography, ultrasound, and fluoroscopy. Even small internal defects, invisible to the naked eye, can compromise performance and safety. The industry has developed rigorous quality control standards that ensure only perfect components are installed in operational engines. The training of metallurgists and materials engineers specialized in superalloys is itself a long-term undertaking. Mastering the complexity of these materials requires years of study and practical experience. Prestigious universities around the world offer specialized programs in materials science and engineering, where the next generation of specialists learns not only the fundamental theory, but also the practical arts of processing, characterization, and application of advanced materials. Many of these students will eventually find careers in the aerospace industry, contributing to the continued advancement of superalloy technologies. Intellectual property surrounding superalloys is fiercely protected. Each engine manufacturer has its own proprietary compositions, developed over years of research and optimized for their specific applications. The exact recipes, the detailed processing procedures, and the manufacturing techniques are carefully guarded trade secrets. This competition drives innovation, with each company seeking to surpass its rivals through the development of superior materials and processes. The environmental challenges associated with the production and use of superalloys are also receiving growing attention. The mining and refining of the rare elements used in these alloys have environmental impacts that cannot be ignored. The industry is responding through the development of cleaner and more efficient production processes, increasing recycling rates, and the search for alternative compositions that depend less on problematic elements. The goal is to continue providing the high-performance materials that society needs, while minimizing the environmental impact of their production and use. When we think about the future of aviation, whether the transition to more sustainable fuels, the development of hypersonic aircraft, or even deeper space exploration, superalloys will continue to play crucial roles. Each of these future advances will present new materials challenges, and metallurgists are already working to anticipate and solve these challenges. The quest for better materials is an endless journey, because there will always be the desire to go faster, farther, and higher. International collaboration in materials research continues to be vital. Scientific conferences bring together researchers from around the world to share findings, discuss challenges, and collaborate on projects. Although commercial competition is intense, the fundamental scientific community recognizes that progress is accelerated when knowledge is shared. Publications in prestigious scientific journals disseminate new discoveries, submitted to the rigor of peer review, ensuring that only solid and reproducible work contributes to the body of collective knowledge. Computational simulation techniques are transforming the way new superalloys are developed. Sophisticated models can predict how different compositions will behave under extreme conditions, reducing the need for expensive and time-consuming cycles of trial and error. Molecular dynamics can simulate the behavior of individual atoms under conditions of stress and temperature. Finite element models can predict how entire components will respond to complex loads. These computational tools do not replace physical testing, but allow researchers to focus their experimental efforts on the most promising compositions and designs. Advanced materials characterization reveals increasingly deep insights into how superalloys work at a fundamental level. Modern transmission electron microscopes can visualize structures at atomic scale, allowing scientists to directly see the hardening precipitates and other aspects of microstructure. X-ray and neutron diffraction techniques provide information about crystalline structure and how it changes under strain and temperature. Spectroscopy in various forms reveals the local chemistry at different phases and interfaces. Each of these techniques contributes to a more complete understanding of how these remarkable materials achieve their exceptional performance. The cost of the most advanced superalloys is substantial. A single crystal turbine blade for a large jet engine can cost tens of thousands of dollars to produce. The high cost reflects not only the value of raw materials, particularly rare elements like rhenium, but also the complexity and precision required in processing and manufacturing. For military engines or commercial aircraft, where reliability and performance are absolutely critical, these costs are considered necessary investments. However, there is always pressure to reduce costs through process improvements or more economical alternative compositions. The logistics of supplying the necessary elements for modern superalloys is a complex global undertaking. Cobalt may come from the Democratic Republic of Congo. Rhenium, a byproduct of molybdenum mining, may come from Chile or the United States. Chromium comes mainly from Kazakhstan and South Africa. This global supply chain needs to be carefully managed to ensure reliable flows of essential materials. Disruptions in the supply of any critical element can have cascading effects throughout the aerospace industry. Safety considerations surrounding superalloys are rigorous. For safety-critical components like turbine blades, each batch of material is meticulously tracked from its initial production through each processing step to final installation. If a defect is discovered in a component after installation in an operational engine, it is possible to track all other components made from the same batch of material and inspect or replace them preventively. This level of traceability is essential to maintain the extraordinary safety standards that have made aviation one of the safest forms of transportation. Looking at what has been achieved since those early days when American observers first saw the potential of new alloys, it is evident that the journey of superalloys is one of the great success stories of applied science and engineering. Materials that could barely maintain their shape at temperatures of 1,000 degrees gave way to alloys that routinely operate above 1,200 degrees. Components that failed after hundreds of hours of operation now function reliably for tens of thousands of hours. The transformation in capabilities is truly remarkable. This story also reminds us that technological progress is rarely the result of isolated genius, but rather the product of collaborative and cumulative efforts. Each advance in superalloys built on foundations established by previous work. The metallurgists who developed the first nickel-based superalloys were relying on decades of prior knowledge about nickel alloys and special steels. the developers of single-crystal alloys built on the foundation of polycrystalline superalloys. And researchers working at current frontiers are building on everything that came before. It is a beautiful illustration of how science progresses, not through uncoordinated leaps, but through a steady climb, where each new plateau reached becomes the platform for the next advance. For all of us who benefit from modern aviation, whether traveling the world or simply knowing that military aircraft protect the skies, there is a debt to those scientists, engineers, and metallurgists who dedicated their careers to understanding and perfecting these remarkable materials. Their work, largely invisible to the public, made possible the modern era of aviation. Each safe flight is a testament to their knowledge, skill, and dedication. As we look to the future, we can have confidence that the same principles of rigorous investigation, careful experimentation, and ingenious application that led to past advances will continue to drive future progress. Tomorrow's materials challenges, whether for hypersonic engines, advanced space propulsion, or applications we have not even imagined yet, will be faced by a new generation of materials scientists armed with even more powerful tools and building on an even deeper foundation of knowledge. The story of superalloys is far from over. In fact, the most exciting chapters may still be to come. And so, when we look to the sky and see the condensation trails of a jet flying high, we can appreciate that aircraft is flying thanks to materials that were imagined, developed, and refined through decades of dedicated work. The engines that propel it contain some of the most sophisticated materials ever created by humanity, operating under conditions that seem to defy the limits of the possible. And it all began with the shock and admiration of observers who realized they had witnessed something truly revolutionary, an alloy that could let jets survive the extreme heat of combat. May we always have the wisdom to value and continue to develop such remarkable achievements, recognizing that they are products not only of human intellect, but also of the gifts of creation that the Lord God has granted us to understand and use wisely.